Hello, welcome to Mechanical Engineering / EMA 540. Coming to this class, you've already had a class on vibration theory, and now you're going to learn how we do experiments. This will strengthen your mastery of vibration concepts and also teach you a skill that can be used in the real world. The first question that you might be asking is, should I care about vibrations? What does it have to do with real life? There are usually three main reasons that people care about vibration, and we'll go into each of these quickly today. First is that it makes things break. Vibration loads, steady vibration, repeated stress over and over again can cause all kinds of things to break. For example, this turbine engine, as this rotor spins, as the turbine spins, the blades can vibrate, and that vibration induces stress on the blades, and a lot of engineering has to go into designing those blades to make sure that they don't break in operation. Other places, exciting loads that you might see in aerospace type industries. This is simulation of a separation load where the front cone of a rocket is being separated from the rocket body. And so this is a violent event, and we have to make sure that any electronics or anything that we put in this rocket that we're hoping to use survive that blast. Similarly, flying machines are subjected to aerodynamic loads. So those can be kind of like impacts, or they might be more steady loads, random loads due to turbulence in the atmosphere. So we need to design things to survive these types of loads. Another reason that we sometimes care about vibration is that we want to control the type of noise or sound that something makes. A speaker is something that converts an electrical signal into a mechanical vibration of this plate, and that plate transmits sound into the air. And a lot of engineering goes into designing these speakers so that the sound that arrives at your ear is as close as possible to the electronic signal that you started with. So a lot of really interesting engineering in that. Cars are designed to be quiet or to have a certain quality of sound. For example, if you took this Lexus and started it up, and it sounded like this, then you might be excited, right? It sounds like a powerful car. This is a sport car. You want to have a good engine, good quality of noise. It's not just about being quiet, but it's having a certain quality of noise that communicates something to the person who buys it. Conversely, if you buy a Harley Davidson, right, you have totally different goals. There you want a lot of noise, a lot of shaking, a lot of vibration. That's kind of the trademark of one of those motorcycles. So products distinguish themselves based on how they sound. Oops. The last area of vibration is making sure things move in the right way. Some really fun applications of this are sporting goods. A golf club, you can see in this photo that a golf club is a flexible shaft with a head on the end, and the shaft's only job is to get that head aligned with the ball and to accelerate the head up to greater than 100 miles an hour as it hits this ball so that we get the trajectory that we want. So there's actually a flex and a loading and unloading of the golf club shaft that happens during a swing. And so you want the flex to be just right such that the timing of the loading and unloading is perfect, and there's no energy stored in the shaft as the head approaches the ball, but all of the energy has been converted to kinetic energy or velocity of that club head. So not just sporting goods though, robotics is another example of areas where this matters. Things like clearances and pumps, fans, all of these have moving parts that need to move in the right way to make things work. So those are the reasons why we need vibration in general, both theory and experiment. Why do we need experiments? There are two major kinds of experiments that are used in industry. One of them we call qualification tests. And these are tests where we shake something to see if it will break, to see if it can survive all the shaking that we need to subject it to during its life. So this little video shows an example of a shake test that was performed on the Orion spacecraft. So this brown part is the Orion spacecraft. The blue part up there is not actually part of the vehicle. That's just a fixture that was attached during the test. And you can hear the vibration, you can see the violence of it, you can see the flexing, some of the deformation that's happening here. Let's see that one more time. So, these kinds of tests are very noisy, high amplitude. This is a huge facility in Ohio with this massive shaker powered by, many hydraulic pumps to be able to provide an environment that's kind of like what this spacecraft will see when it's on a rocket later and it flies to space. What you see here is the actual flight hardware being tested. And so we're verifying that the hardware can survive. We're seeing how the hardware will perform in the actual environment. So this is an example of a qualification test, and this happens to be a test that I've been involved in the results of and understanding what the data from that test meant. So that's the first kind of test, shake it and see if it breaks. This class will actually focus on the second type of test, which are called validation tests. And usually we do these because we have some kind of model, usually a computer model, a finite element model, and we want to make sure that that's accurate. For example, almost all airplanes, to be able to fly, anything that the FAA approves, has to have a ground vibration test. So there would be a model of this airplane. This is a NASA experimental airplane studying blended wing and other concepts. But before it's allowed to fly, we actually have to do a test to see if the finite element model matches what we think it matches the actual hardware. Only then do they allow the airplane to fly. If we didn't do this, it could be dangerous because the aircraft can encounter something called flutter, where the aerodynamic forces over the wing cause them to shake violently and can even cause them to be torn off. And so we need to know that the airplane is safe and what speeds we can expect to fly it to. And so this is done by performing a ground vibration test. And this picture shows an airplane with everything mounted, ready for test here. So this is an important kind of test, and this is really what we focus on in this class, kind of having some kind of model and comparing that with the test. You would think in 2020 or whatever year it is today as you're watching this video, that computers are so powerful, why should we even need testing anymore? But experience has shown that a complicated structure like this, or even more complicated, might be a rocket or launch vehicle or some other structure. But on a complicated structure like this, there are almost always problems with the model. We do our best, but there are a lot of unknowns. There might be materials we're not quite sure of the properties. There might be geometry that we have to approximate to be able to mesh it without requiring too much computational cost. Or there might just be things that are overlooked, brackets that we approximate one way that we find later that wasn't necessary. So experience has shown over and over again in the launch industry especially that this testing is critical. And so often it's required, and it's an integral part of the design of the vehicle. There's design, testing to make sure that what we built is really what we wanted, and then further simulations to see about the survival before we finally have prototypes. So the type of testing that we're going to learn about in this class is basically identical to the types of tests that are used in modern aircraft ground vibration tests, or all of the hundreds and thousands of other tests that are done in industry every day to diagnose vibration problems or different things. So you'll leave this class hopefully with a skill that you can immediately use in the real world in a job, if you're so lucky as to get a job where this is done. There are other kinds of tests that are done that I'll hit on quickly, and the things you learn in this class will help, though we won't directly do a lot of this. But testing is also used to characterize materials. So if we have a material that's new and we want to know what its stiffness is, what its its mass distribution, properties like that, we might do vibration test. It's also used in a device called an atomic force microscope. So here you have a little tiny cantilever beam that's vibrating over a sample, and that beam has a very sharp tip. The tip comes down to often 10 to 20 nanometer radius, so to where it interacts only with maybe a few hundred atoms or so. And one of the most sensitive ways to use this device is to actually cause the tip to vibrate steady state over a sample, and then monitor the phase and the amplitude of vibration. And then we map this, then we sweep this tip over the surface while holding, say, a constant phase or a constant amplitude of vibration, and you can get incredibly high resolution images of surfaces. This is the type of testing that was first able to actually image an atom, or see an atom that was missing from a lattice of a crystal, down to this atomic scale. So interesting stuff that can be done with vibration and testing. It's also used a lot in the medical world, in ultrasound imaging, characterizing tissues. These pictures are from a project I was involved in where we were using wave propagation in the Achilles tendon to try to measure the force in the tendon. So we found that if we had two sensors and we sent a wave up the tendon, we could see a delay, measure the time it takes for that wave to propagate. And that can then be used to calculate what the load is in the tendon. And if you do this quickly enough, you can do it real time as someone's running and actually look at how their technique or the shoes they wear or different things like that are affecting the stresses that tendon is seeing. So the pilots for this project were actually first done in an EMA 540 final project. So the kinds of tests that you do in this class are relevant to the real world. Vibration is also used to try to detect damage. This was actually part of my PhD research. I took measurements that someone else acquired from this highway bridge in Switzerland. So this is an animation derived from the measurements. And they took measurements and then they did various damages to the bridge. The bridge was going to be taken down anyway to make room for a bigger one. And so they did little bits of damage and then repeated the test, and from that we're able to show how the vibrations change with damage and whether or not you could use vibrations to detect damage or have an early warning that the bridge might be near failure. We also used a similar approach at the other end of the length scale. What you see here are 1 centimeter by 1 centimeter square computer chips. And they have something like about 100 solder joints holding them to a circuit board. And here we used lasers to measure vibration on the computer chips and measured the deformation pattern. This shows how the edges of the computer chip were deforming. We didn't have any measurements in this case in the center of the chip. And we used these measurements to try to see if some of those solder joints had become disconnected. So another interesting application there. So this is just the start, though. There are all kinds of applications of vibrations. And your first homework problem will actually be to go do some research and see what might be of interest to you. So the way you're going to do this is do a search, and there's a great trade magazine called Sound and Vibration, snv.com. So you're going to just type in snv.com and then then some topic that you're interested in. Say it's a violin. And it will take you to articles within snv.com, hopefully. Oops, that one failed. Maybe they've updated their search and this no longer works. Okay, yep, so here we found an article. And so notice it's taking us to articles on snv.com, and right away you get a PDF of the article. And so we can learn something about what was done. These articles are all written for a practicing engineer, someone without a lot of specialized knowledge. And so they're typically written in a very accessible way where you can get the big picture of what was done without having to have a lot of expertise. So I think you should be able to understand them well. So there's all kinds of different applications here. Let's see. Yep, so for example, for a guitar, here's a bunch, here's some more articles. So again, you can read and see what was done and what kinds of tests and measurements were done. So your homework assignment is to go look at that and to begin to understand how vibrations are used in industry. When we meet in online, we'll have introductions, so be prepared for that. And we'll also review the syllabus in person. That way we can, I can answer any questions that you have about how the class will run, and hear any feedback that you have, any ideas, to make sure that this semester goes on successfully. The last thing I wanted to mention before we close out this lecture is the final project. This class points towards doing a final project, which is a test of some sort that will be very much like the ones that I've kind of told you about already, tests that are done in the real world. So this is what we're aiming for. You're trying to get the skills that you need to be able to do a test like this and understand what the results mean. So some examples, this was a fun project. A student who came to the class actually was working at a company that built this mass spectrometer. It's an instrument that uses a laser interferometer to measure compositions and things. Anyway, they found that their design was working well, only if the technician was singing during the measurements, they would get some extra noise. And they didn't want that. That meant that their system was too sensitive to noise. So they came in and they actually instrumented and did a test on this component, and were able to correlate that with a computer model and figure out how they could then modify this to stiffen it up and eliminate the vibrations. Another fun project that one group did was analysis of a golf club shaft. So in this project, they studied, they measured the vibrations of golf club shafts that were kind of held really lightly, and they looked at how that changed if you were gripping the club tightly. That's more like the actual operation condition. And then they even ended with some tests where they actually measured the vibration of the shaft. This is flexing of the shaft during a swing. And here you can see the ideal scenario where the shaft is loading, unloading, only in this case it unloads and it goes beyond the unloading point, and the impact happens out here. So they were able to see that this shaft was actually not tuned correctly for the swing speed of the person who was using it. So another fun project that was done a few years ago was a ground vibration test on a private airplane. This was a sport plane built from a kit, and we're able to apply instrumentation and do a test to try to measure some of the fundamental bending modes of the wings of the airplane. And they used this to try to see what the maximum speed of the airplane might be. Now this was a sport plane, it was very stiff, and so everything we found was that this plane was safe up to pretty high speeds, well beyond what it was capable of flying. This course is going to be a blended learning course. I'm assuming you come in with some knowledge of vibrations, but all of you are coming in with a different amount. And the best way that I've found to address that is for us to spend time working through problems. And so we will have lectures online, or we will have some reading assignments, and we'll spend a lot of the class time actually with you working problems, working homework problems. Because that's where the learning really happens. If you sit and listen to this video, what you actually gain from this won't be very much in the end, unfortunately. But if you actually sit down and solve a problem, do one of these labs, for example, your learning is, many times greater. So we're going to model this class after that type of approach. We're going to, again, try to spend the class time working on homework in an environment where you can ask each other questions, you can ask me questions, and get through those assignments, which is where the learning happens. So that's the approach that we're going to use, and that concludes this first lecture, and we will see you in class, where we will meet in person and continue the discussion.